Good morning, everyone. Today our lecture is going to be on the applications of normal distributions. In our last class, of course, we introduced a normal distribution, which is commonly referred to as a bell curve. And we saw that it has all these nice properties. In particular, it's symmetric with respect to the mean. The mean is going to occur exactly in the middle. So it's going to look like this. And here's our mean mu. And we found out that a certain percentage of our curve is going to occur within 1 standard deviation of our mean. So to the left, subtract 1 standard deviation. To the right, add 1. Over here, 2 standard deviations away, and so on. So we're going to expand upon that idea a little bit. We're going to refer now to the standard normal curve, and I'll explain what that is in just a little bit. But I want to remind you that our learning objectives for the day are to compute probabilities for a given value of any normal random variable. And conversely, if we have the value of the random variable, if we have the probability, we're going to compute the value of the random variable. So what do I mean when I say standardizing a normal random variable? So essentially, if we have some weird standard deviation, like in our first example here, the standard deviation is going to be 10. Rather than adding units of 10 to the left and right, as we were doing before, we're going to make it so that we just add units of 1. So we're going to use the letter Z to represent our standard normal table. And it says here that any random variable x can be transformed into the standard normal random variable z using this formula. Z is equal to, if we have a value for x, we can plug it right in here. If we have our mean and our standard deviation, we can get back a value for z. On the other hand, if instead we have a value for z, then we can plug it in here to the second formula and get back our value for x. So we're going to be doing that a lot. So I'm going to show you a very powerful tool that we have here, which is the standard normal table. So once we convert it in terms of z instead of x, then we can simply refer to this table. All of these small numbers here on the inside of the table are probability values, and z is the number of standard deviations away from the mean. So you'll see the probability, like in this first corner, of being 3.4 standard deviations less than the mean is very, very small. It's 0.0003. So you will see from this picture in the top left corner that this table gives us the area going from left to right. We can also use this table to talk about the area that's on the right-hand side of a value. We just have to do a little adjustment. Can you think of what that adjustment might be? Well, if we're looking for this area instead, say, we know from our last lecture that the total area under this curve is 1, corresponding to the probability of 1. So if we're looking for this area to the right, but the table only gives me the area to the left, I can use the table to find this area on the left and then subtract it from 1. So it would be 1 minus area on the left is area on the right. So this one table is going to meet all of our needs for talking about normal distributions. So let's start with an example. In each of the following problems, we're going to use that x is a random variable normally distributed with mean 70 and standard deviation 10. We're going to draw the graph of the normal curve with the desired probability and value, and find the indicated values of x. So number one, we're looking for the value of x larger than 95% of all x values. And all we know is that x is a normally distributed random variable with mean 70 and standard deviation 10. So let's start by drawing our nice curve. So nice bell-shaped curve as before. And I know if I'm looking for an x that's larger than 95%, it's probably going to be way out here, the 95th percentile. And all of my smaller x values are this area on the left. Well, that's great because my table tells me the area on the left, so I'm going to use my table to find a z-score. And then I know that if I have a z-score, I can find the value of x using this formula. So let's start by finding a value for z. Back over to my table here. So I'm looking for 95%, and I know that at the top of the table, these values are really, really small, 0.0003 and so on. So I'm going to keep going down. You'll see that I've highlighted some certain values here. These are the values that we'll need for this lecture, so I went ahead and found them for us to save time. So here we are. I'm looking for 95%. I find out that the closest I can get is either 94.95% or 95.05%. So the process that we're going to use whenever we run into this situation is we're going to take the average of the two z-scores. So let's find out what the two z-scores are. I'm in this row 1.6, and I'm going to count from left to right. This is 0, 1, 2, 3, 4, and 5. So these are 1.64 and 1.65 in terms of their z-scores. So let me go back to our problem. We're going to use that information that we just read from the table. Okay, so I found out that z is between 1.64 and 1.65, and I said when we're between two, we're going to take the average. So taking the average means I'm going to add them and divide by 2 since there are 2 of them, and I'm going to find out that my z-score that I'm going to use is 1.645. But the problem asks me for the x value, so I need to go back and remind myself, how do I go from z to x? Well, I'm going to use this formula. X is equal to z, so that's 1.645, times the standard deviation, sigma, times sigma, plus the mean mu. So that's 1.645 times 10 plus 70, which is equal to 16.45 plus 70, and that's equal to 86.45, which answers my question. So I can say that the x value for this normally distributed random variable that is larger than 95% of all the others is 86.45. So let's practice a few more of these. How about the x value smaller than 97.5% of all x values? Well, smaller is a little bit more challenging, because if I draw my normal curve, I'm saying that 97.5% of all the x values are over here. And here I am, this is the x I'm looking for, and it's smaller than 97.5%. But we already know what we need to do. We need to do 1 minus. So first, I'm going to convert 97.5% is in decimal form, so it corresponds to the decimal 0.975. So I want to do 1 minus 0.975, and I find out 0.025 is that number. So that means that this area on the left is 0.025. And I know that my table gives me area on the left, so now I'm good to go. I'm going to look for that z-score. So going back to my table, and I scroll back up because I know the smaller probabilities are higher up in the table. And fortunately, I have exactly 0.025 here in my table. So again, I'm going to count from the left. I know that I'm in the row corresponding to negative 1.9. This is 0, 1, 2, 3, 4, 5. So this is negative 1.96, the z-score that I'm looking for. And negative 1.96 is going to give me exactly 0.025 on the left, and that's 97.5% on the right. So go back to my problem, and I say the z-score that I found out is negative 1.96. And I know how to use that to find x. Negative 1.96. This is the number of standard deviations away. So we're 1.96 standard deviations to the left of the mean. So I multiply that by the value of standard deviation, and then I add the mean. So I get negative 19.6 plus 70, which is 50.4. So that is the answer I was looking for. Whoops, I apologize. The x value smaller than 97.5% of the other x values is 50.4. How about the 0.5th percentile? The 99.5th percentile. Okay, so we're looking for, let's draw our curve again. So I would recommend that drawing the picture should pretty much always be your first step, because this is going to allow you to understand what you need to look for in the table. So the area on the left should be 0.005. Because that's 0.5%. Over here, 1 minus 99.5 is also 0.5, so this is also going to be 0.005%. Okay, so we're going to go to our table, and we're going to say, let's start with this one here on the left because we know we can read our table that way. We're looking for a z corresponding to 0.005. Again, I see that I'm sort of between two values, and I know that means I'm going to take the average of those two. And if I count, I can actually see the top of the table here, which is kind of nice. So I'm in the minus 2.5 column, and I am between negative 2.57 and negative 2.58. So I'm going to go ahead and say that my z value is the average of negative 2.57 and negative 2.58. And I know how to find that average. Z is minus 2.57 plus minus 2.58 and divided by 2. So So that should be minus 2.575. And I can plug that into my formula. That means x is equal to minus 2.575 times 10 plus 70 equal to minus 25.75 plus 70 equal to 46.75. So here, x equal to 46.75 is my 0.5th percentile, meaning that it's larger than 0.5% of x values. The problem also asked me to find the 99.5th percentile, and we can see from our picture that it's symmetric to the other side. So using the symmetry of this thing, I don't even have to do 1 minus, because if I did 1 minus 0.995, I would find out that that's 0.005. And I already know that guy. So what do I do using the symmetry of the table? I'm just going to change my negative 2.575 to positive. And if we think about this idea of how many standard deviations away from the mean, if I'm here, I'm negative 2.575. So by the symmetry, if I'm here, I'm plus 2.575. So let's make the necessary adjustment. For the other one, we're going to say positive 2.575 times 10 plus 70, and that's equal to 25.75 plus 70, which is equal to 95.75. So just using what I know about the symmetry of the normal distribution, I can say when x is equal to 95.75, it's bigger than 99.5% of the other x values, or it's the 99.5th percentile. So you can clearly start to see why this is such a powerful method. Okay. So the two symmetric values of x that contain the central 98% of x values between them. Again, let's start with a picture. Bell curve. And I'm looking for two values of x, symmetric. So maybe one over here on the left and one over here on the right. So that in between them is 98%. So if I'm accounting for 98%, how much is left over? Well, 1 minus 0.98 is equal to 0.02. But I need to split that up between two sections. I need half of it here on the left and half of it here on the right. So I'm going to divide by 2. So I want 0.01 or 1% here on the left-hand side, and I want 0.01 on the right-hand side as well. And now it looks quite like the last problem, and we know what to do. We go to our normal table. We're looking for 0.01. So I scroll down, and again I find I don't have exactly 0.01, so I know I'm going to take the average of these two values, and these are minus 2.32 and minus 2.33. Back to my problem. Minus 2.32 minus 2.33, add them up, divide by 2, minus 2.325 is the z-score that I'm going to use. And as in the last problem, I'm going to say that this x over here on the left, I'm using the negative z-score, the one that I found, because the table gives me area on the left. Whoops. So starting with negative 2.325 times 10 plus 70, and I know that that's minus 23.25 plus 70, which is equal to, this one is 46.75. So I apologize up here. I made a typo because I was doing the wrong problem. You might have caught that as you were watching this video, so let's fix this here. 70 minus 25.75 is 44.25. So I apologize there. The rest of the work is the same, and this value 95.75 is correct. Okay, so back down to number 4, 46.75 is the x value that corresponds to 0.01. And from the last problem, I know that using the symmetry of this table, I can do 23.25 times 10 plus 70. Whoops, 0.2325 times 10 plus 70, which is going to give me 23.25. 2.325 times 10, that gives me 23.25 plus 70, which is 93.25. So 93.25 is the other x value. So now I have two symmetric x values that 98% of the data is contained between them. Exactly what I wanted. Answers my problem. So moving on, let's do another type of example. This is called hungry babies. So 6-week-old babies consume a mean of 15 ounces. I know that I need a mean, so let's go ahead and highlight that. A mean of 15 ounces of milk per day with a standard deviation of 2 ounces. Highlight that. Assume that the distribution is normal, of course. Find the probability that a randomly chosen baby consumes the following amount of milk per day. So A, less than 15 ounces. Let's start with A. So as usual, I'm going to draw the bell curve. That's going to help me visualize what it's talking about. It told me that the distribution is normal. That's very important. If you have a question and it doesn't say that it's normal, then we might not be able to use this approach. So I have my normal curve. I'm looking for less than 15 ounces. So it sounds like I'm given, excuse me, I'm given a number in ounces. The random variable x corresponds to ounces. I want to use the standard normal variable z, which just talks about how many standard deviations away I am. So I'm thinking I'm probably now going to be using this second formula, z equals x minus mu over sigma. So let's write it here. Z equals x minus mu over sigma. That means if I know an x value, like 15, I can find a corresponding z value. So then z, there we go. So z, so 15 is the x. I want to subtract the mean of 15. and divide by the standard deviation of 2. So this is 0 over 2. So for part A, I'm talking about 0 away from the standard deviation. And well, hey, we already know that that's the mean. So I could have just observed from the beginning that the value that it gave me, 15 ounces, is equal to the mean. Or we can always plug it into this formula, and when we find 0, we find out that since this is the mean, it's exactly here. Because of the symmetry of this curve, we know that probability should be 0.5. Should be exactly 50% chance. But if we weren't sure, we can confirm that by looking at our table. So we found the z-score of 0. That is on my table. It's here in the bottom left corner. Negative 0.00 is 50%. Also, positive 0.00 is 0.5. Great. So that answers part A. We know that. Probability is 0.5. And how do we write that? We should say the probability that our x is less than 15, because the problem said less than 15, is 0.5. We know that when we're talking about a probability, it's always a number between 0 and 1. So we want to make sure we don't write 50 here. That would not be correct. We use the decimal version, 0.05. All right, great. So part B, more than 17 ounces. Okay, well, from the picture in part A, I know that the mean is 15. So more than 17 here's 15. 17 is somewhere here. And we're talking about more than 17. That looks like it's the right tail of my distribution. So first of all, let's use our formula. If we know an x, we can find a z. We're just going to use 17 for x minus the mean of 15 divided by the standard deviation of 2. So 2 divided by 2 is 1. So I'm saying 17 is 1 standard deviation away. But in terms of this probability, we know that it's going to be 1 minus whatever this probability is. So 17 corresponds to z equals 1. So we need to do 1 minus the probability when z equals 1. Let's go back to our table and see when z equals 1. The probability is 0.8413. So 1 minus that should give me my answer. So probability that x is less than 17 is 0.8413. That's 84.13%, but I'm going to use the decimal because I'm talking about a probability. My number should always be between 0 and 1. So then, since what the problem actually asked me is probability that x is more than 17, I say, well, that's just 1 minus the probability that x is less than 17, which is 1 minus 0.8413, which is 0.1587. So part B is taken care of. Let's see if we can squeeze in a part C. Part C is asking us between 17 and 19. So I already have some information about 17, that's good. My picture. 17, 19. Those are x values. I want to convert them to z values. I know that the z value corresponding to 17 is already 1. So let's see about 19. Z is equal to the x value minus the mean divided by the standard deviation. So z is 2. That means I'm 2 standard deviations to the right of the mean. Look in my table. What corresponds to z equals 2? Well, it's 0.9772 here. So I'm going to use that in my problem, as well as what we already found out in the previous part. So, probability that x is less than 19 is 0.9772. That probability, though, corresponds to this entire area. And I only want this little blue rectangle. So that means I want to take the green area and subtract the area less than 17. So we already know probability that x is less than 17. So how about this? Probability that x is between 17 and 19 should be probability that 17 is less than x is less than 19, first of all. And from the picture we can see that that should be equal to the probability that x is less than 19, subtract the probability that x is less than 17. And I know those two numbers. I know that's 0.9772 subtract 0.8413. So I have 0.1359 is the probability that I'm in this blue rectangle between 17 and 19. And that's the answer to my question. All right. So here's another question. Find the amount of milk x greater than 95% of all values of x. Find the amount of milk x less than 95%. Compute the two symmetric amounts of milk that contain the central 90%. Okay. So step by step, let's see. A. So we're still using the information from up here. We know that our mean is 15 ounces. Our standard deviation is 2. So mean is 15 ounces. Standard deviation is 2. Let's take a look at what it's asking us. In terms of our picture, here's my curve. So first of all, find the x greater than 95% of the others. So I know that that should be here, the 95th percentile, something like this picture. And all the x values that it is greater than are here to the left of it. And that's how my table works. It gives me this left area, so that's nice. So I want to go back to the formula we were using on the first page. Now I'm given with a percentile or a probability. I need to find a z, and then I need to find the x from that z. All right. So which z corresponds to 95%? Going back to my table, we've already used this one. We're going to take the average of 1.64 and 1.65. We know that's going to be 1.645. So some of these, like 95%, are commonly used. You'll probably use them enough that you get to just remember them. So z is between 1.64 and 1.65. Our rule is that if it's anywhere between, we take the average. We get 1.645. That's going to correspond to this 95th percentile x. but I need to convert it to x's, so I say it's z times the standard deviation. We know that z talks about the number of standard deviations, so this makes sense. I'm going to multiply it by standard deviation, and then I'm going to add the mean. So that's going to give me 3.290 plus 15. And that is 18.290. So 18.290 is the x value greater than 95%. That was the first part of the question. Okay, the second part of the question, what about the x value less than 95%? So what if instead I'm talking about the 95% now is over here, and I'm just looking for this 5% here. Well, we know from past experience we can use the symmetry of this table, symmetry of this bell curve rather, and I can just change this positive z-score to the negative z-score. If I wasn't so confident about that, I can check my table. So the first thing to do to check the table would be to do 1 minus 0.95. So 1 minus 0.95, that's where I got this 0.05. Look it up in my table, and I'm going to find out that it's between negative 1.645 and negative 1.64 and negative 1.65. So let's see that. Here we are, 0.05, 0.04. We don't have exactly the one we're looking for, so we take the average. Average of negative 1.64 and negative 1.65 is negative 1.645. So my z, negative 1.645, I found it from the table, but I also know it because of the symmetry of the bell curve. So I'm going to plug it in to my formula, negative 1.645 times the standard deviation plus the mean, negative 3.290 plus the mean. So that should be 11.71. So 11.71, let's see how they worded it here, less than 95%. And that's less than 95% of x values. Okay? And then finally, the problem asks us to kind of combine this information together and compute the two symmetric amounts that contain the central 90%. So I want this central portion to be 90%. That means whatever's left over, so 10%, I need to split it up between the left side and the right side. So I divide by 2, I get 0.05. And I already know from part A the x value that corresponds to this 0.05. And I already know, I'm sorry, that's from part B. I already know from part A that if this is also 0.05, the x value that corresponds to that is 18.29. Okay? let's see our next question. So let me just do one thing. Let me remind us that this was part B and this was part C. And so our answers for part C are here. Okay, next question. The National Center for Education Statistics reports that mean scores on the standardized math test for 8th graders in 2009 increased slightly from those for previous years. The mean score in 2009 was 283. So what am I going to do? Mean score was 283. Keep that in mind. Assume that the standard deviation is 10. Keep that in mind. Find the probability that the test score of a randomly selected 8th grader was greater than 290. So to find the probability using our table, we need a z-score. What we have is an x, so x is equal to 290. I want to find a corresponding z. Then z should be equal to x minus the mean. So we can think of that as how far away am I from the mean? And then divide that by the size of one standard deviation, and that's going to tell us how many standard deviations away we are. So we have 7 over 10 equals 0.7. Z value is 0.7. I'm going to use that in the table. That means I'm 7/10 of one standard deviation higher than average if I score 290. So let me find out the probability corresponding to 0.7. It's 0.7580. And the Z table gives me area to the left. So the probability that x is less than 290 is 0.7580. Again, I have a number between 0 and 1 because I'm a probability. But I was asked about the probability that the score was greater than 290. So I know what to do there. I say, well, the probability that x is greater than 290 is equal to 1 minus the probability that it's less than 290. I already know that value. That's 1 minus 0.7580. So that should be 0.242. The probability, 0.242, that the test score is higher than 290. That's part A. Part B. What proportion between 295 and 300? So 295 should be somewhere higher than 290, and 300 also here somewhere. So I'm looking for that kind of an area. Well, first of all, I need z-scores. So let's convert these numbers. So when we're talking about the z-score for 295, and sometimes when you're calculating more than one z-score in a problem, to help you keep track of them, it might be helpful to write z subscript 295, so we know that this is the z-score corresponding to 295, and similarly I'll do z subscript 300. So that's 295 minus 283 divided by 10, which is 12 divided by 10, which is 1.2. I also am going to need to find the z-score corresponding to 300, so let's call it z sub 300. 300 minus 283 divided by 10, 17 over 10, 1.7. So we're saying, what is the probability that our test score is between 1.2 standard deviations higher than the mean and 1.7? So the probability that x, pardon me, I want to start with the probability that 295 is less than x and x is less than 300. Well, that should be the probability that x is less than 300 minus the probability that x is less than 295. Can you see that from the picture? Less than 300 should be all of this area, and less than 295, that much. So if I subtract them, I get what I want here in the middle. Okay? And so that we can convert in terms of z so that we can use our table. So that's the probability that z is less than 1.7 minus the probability that z is less than 1.2. I should be able to find those numbers in my table. Let's see. 1.7 is here, 0.9554, and 1.2, 0.8849. So let's go back to our problem. That should be 0.9554 minus 0.8849, which is 0.0705. Did I get those right? I think so. Okay, so the probability of having a score between 295 and 300 is 0.0705. Last question. Oh, no, not the last question. Part C, students who scored at the 5th percentile or lower could not graduate. Find the 5th percentile test score. So what we've done so far is if we know a test score, we found the percentile. Now, 5th percentile, put it up here. Fifth percentile, we know what that looks like. We know we're talking about the probability to the left. We know that we need to find the z-score. So I go to my z-table. I'm looking for 0.05 because that's the 5th percentile. And this should be one that we've already found. 0.05, we need to take the average of negative 1.64 and negative 1.65. We know how to do that. So our z is going to be minus 1.64 plus minus 1.65 over 2. We know that's minus 1.645. And we just need to convert that into the test score. We need to convert from z to x. So we say that x then is 1.645, that's the number of standard deviations. We multiply by the standard deviation, which is 10, and we add the mean, 283. So that's minus 16.45 plus 283. And that should give us 266.55. So the problem tells us if you make 266.55 or lower, you cannot graduate. Last question now, question D. Suppose you know someone who scored 258 on the test. Is this unusual? On what do you base your answer? So I believe we talked a little bit about how many standard deviations you are away from the mean, and when are we going to consider something unusual or an outlier. And we said if it's more than 3 standard deviations from the mean, either to the left or to the right, then we'll say it's unusual. So that's how we're going to support our answer. So first of all, we need to know how many standard deviations away is the score, 258. So my x is 258. I need to convert that to a z. So this is z corresponding to 258. Should be x minus the mean over the standard deviation. And that is minus 25 over 10 minus 2.5. Now we know that when we're talking about the normal distribution and we're using z, z instantly tells us the number of standard deviations. So the score, 258, is 2.5 standard deviations below the mean. Which was 283. So although that's a little low, we said that we needed to be 3 standard deviations in order to call it unusual. So we say this is not unusual since it's fewer than 3 standard deviations below the mean. And that's the answer to my question. All right, let's see another example. Using diaries for many weeks, a study of the lifestyles of visually impaired students was conducted. The students kept track of many lifestyle variables, including how many hours of sleep obtained on a typical day. Researchers found that visually impaired students averaged 9.31 hours of sleep with standard deviation 1.32 hours. What do I do as soon as I see those numbers? I circle them so that I remember. Or underline them, highlight them, whatever. In this case, they say average, but we know that average is another way of saying the mean. So mean of 9.31, standard deviation of 1.32. And we assume that it's normally distributed. Very important. So question A, what is the probability that a visually impaired student gets less than 6 hours of sleep? So I would ask myself, is 6 a z-score or an x value? Because it's 6 hours of sleep, that should be the random variable x, which counts the number of hours of sleep. So x equals 6. But in order to find the probability, we need to convert that to z. So that means take x, subtract the mean, divide by the standard deviation, and I'm going to get minus 2.51. We can plug that into a calculator to be on the safe side. So I can open my browser and I can go to Google, find any online calculator that you like, that you trust, and do 6 minus 9.31. That's minus 3.31, and then divide minus 3.31 by 1.32, negative 2.50. Now, since our table only goes to 2 decimal places, we're going to round here based off the third decimal, and since it is higher than 5, 7 is larger than 5, we're going to go ahead and add 1. So instead of negative 2.5, we're going to say negative 2.51. And as we know in the table, that makes a difference. We would get a different answer if we use negative 2.5 than if we use negative 2.51. Okay, so we're using negative 2.51. Now we go to our table. Negative 2.51 is here. And as you can see, it is different from if I use negative 2.5, I would have 0.0062. But I knew that I should round up because I was closer to that one. So I'm taking 0.0060 to be my probability. So go back to my question. Answer should be 0.0060, but I don't have to write that last 0. Probability is 0.006. So pictorially, I'm saying, here's my mean number of hours, 9.31. 6, of course, is way down here. So the probability of being someone who gets less than 6 hours of sleep, very small. It's 0.006. All right, what about the next part? What is the probability that the student gets between 7 and 9.97 hours? So as always, it's going to be helpful to start with my picture. I know that my mean is 9.31. So 7 is somewhere here on the left. I'm not sure how far to go, but I draw it over on the left. 9.97, somewhere here on the right. Probably a little bit closer to the mean than 7 is. And I'm looking for this area in between. So it looks like if I found the area to the left of 9.97, I would have all of this. But I know that I'm getting more than 7 hours, so I don't want that extra piece. I don't want this green piece. So it looks like what I need to do is I need to find the probability that x is less than 9.97 and subtract the probability that it's less than 7. So probability that 7 is less than x is less than 9.97 should be the probability that x is less than 9.97 minus the probability that x is less than 7. Can you see that from your picture? All right. And I know that to find these two probabilities, I'm going to need z-scores. I have x values right now. To use the table, I need z-scores, so let's convert to z. Z sub 7 is equal to 7 minus 9.31, the mean, divided by the standard deviation of 1.32. Again, I can use my calculator here. So I have 7 minus 9.31. That's minus 2.31, and I divide by the standard deviation, and I find out that minus 1.75 is the z-score, corresponding to 7. So 1.75 standard deviations lower than the average number of hours of sleep. I want to do the same thing for 9.97, subtract 9.31, divide by 1.32. So subtract the mean, divide by the standard deviation. I'm going to use my calculator to help me out. 9.97 minus 9.31, 0.66. Divide by 1.32 is 0.5. So those are actually pretty nice z-scores. Half a standard deviation higher than the mean if you're getting 9.97 hours. All right, so I know that I'm looking for the probability that x is less than 9.97 minus the probability that x is less than 7. Translates to the probability that z is less than 0.5 minus the probability that z is less than negative 1.75. Let's find those numbers in our table. So z less than 0.5. I've got to scroll down, 0.5 should be 0.5199. Let me double check my calculation since I didn't highlight that one. Maybe I just forgot it. 9.97 minus 9.31 divided by 1.32, definitely 0.5. And what am I doing wrong? Oh, so I'm reading the table wrong. Here we are. 0.5 is here, 0.6915. All right, and then I also need less than negative 1.75. So I know for 0.5 it's 0.6915, and negative 1.75, here we go, should be this one, 0.0401. These are the two numbers I'm going to use in my problem. So let me go back. And I say the probability that z is less than 0.5, that was the first number that I found, 6915. The probability that z is less than negative 1.75 was the second number, 0.0401. So I need to find out what is 0.6915, subtract 0.0401, and that gives me 0.6514. And that answers my question. All right, the probability that a visually impaired student gets between 7 and 9.97 hours of sleep is 0.6514. Okay, continuing with this same question, 40% of students get less than how many hours of sleep on a typical day? Let's think about that. I know that my mean is right here at 9.31. So 40%, the 40th percentile, should that be to the left of my mean or to the right? To the left of my mean is a total of 50%. To the right is also 50%. So if I want 40%, I want something to the left of my mean. So I'm looking for the x value that corresponds to the 40th percentile. And I know how to find that. I need to convert 40th percentile into a z-score, and then I need to convert that z-score into an x value. So let's see my table. I'm looking for 0.4 for 40% in my table. And it looks like that should be, scroll down, somewhere in this ballpark. But as we've encountered before, we don't get exactly 0.4. So I have to take the average of these two z-scores. And this is negative 0.20, 21, 22, 23, 24, 25, 26. So between negative 0.26 and negative 0.25. So I'm going to need to find the z-score, the average of those two. We know to take an average, since there's just two of them. We're going to add them up, divide by 2. So z is equal to negative 0.25 plus negative 0.26, divide by 2, that's negative 0.255. Okay, I have a z-score, but what I want is the number of hours of sleep, which is in terms of x. So x will be, I take that z-score, the z-score tells me how many standard deviations away from the mean I am, so I multiply it by the value of one standard deviation, and then I add the mean. Okay? Definitely gonna need a little help from my calculator here. So I have negative 0.255 multiplied by 1.32. That's negative 0.3366. I add 9.31 hours to find that 8.9734 should be the number of hours here. So that's 8.9734 hours. And that answers my question. 40% of students get less than this amount, 8.9734 hours. Okay. So it looks like that concludes this lecture on applications of normal distributions. If you have any questions, please email Dr. Doss, and he'll be happy to answer your questions. Thank you.